As we continue on with our sequences and start diving into the actual area problem, let's do a little reviewing. Now, if I asked you for the area of a shape that looks like this, most of us are pretty familiar. Area is length times width, and if we forgot it, we could easily look it up. Now, we know a circle area is pi r squared, or at least we can look that up, but this is half of a circle, so it's half pi r squared. And even if we get to one that we're not as familiar with, but this is a trapezoid, its area is half of the height, and you add up base 1 and base 2. And again, easily looked up, a formula we can find. But now we run into this shape. This is not a rectangle, this is not a trapezoid, this is not a semicircle. It's this curvy shape on top with rectangular kind of sides, but nothing is the same all the way through. It's a very irregular shape. Now there are a couple things that we could try. We could try to make it a rectangle, but if I pick this point to make my rectangle, that rectangle's a little too big. We got some extra area in here that I didn't want. I could make this rectangle right here, but it's a little small. I didn't catch this area right here at all. So I'm caught somewhere in between. So what could we do with this? Well, as we explore this idea, one of the things the book suggests is, what if we did more than one rectangle? What if I took this rectangle to here, and I took this rectangle to here? Now that's better. I've extra space here, missed a little space here, but maybe I go this rectangle here and that rectangle there. Or maybe I go more rectangles. The more rectangles that I can put in here, the better this is going to get. So we're going to come back to this concept. But here's a function you're used to. And I want to look at those two extreme cases. What if I would go right out here to 1? So when I plug a 1 into my function, x squared is 1, so the y value is 1. So this is 1 by 1. When I multiply that, this whole thing is 1 square unit. But if I instead use the small rectangle, which is right here, I end up at 0. And 0 times 1 is 0, and this rectangle has 0 area. My answer lies somewhere between this smallest rectangle and this biggest rectangle. Let's try them with 2. We'll leave this one right here. This is half. And when I plug a half in to that equation, I get 1/4. So a half times a fourth, well, that means this part is 1/8. But again, I have extra up here. I included a little too much. And if I go this one, this is also a half by 1, because this height up here is 1. So 1 times a half, which is a half. And that has a little extra in it. But now I'm at 4/8 and 1/8. This is 5/8. It's way better than 0. And it's way better than 1. It's at least getting closer, but I still have too much in here. And I could go the other route, and I could take one that's got a little too little in there. There's got to be a better way of tackling that. And that's what we're going to attack today, is how do we find the area of this irregular shape that we don't just have a formula for? So let's take a look at an example. Here's my function, and I broke it into 5 rectangles. Now, it's not perfect because I've got some spaces up here that I'm not counting. I'm only counting what's in my rectangles, but I'm pretty close. So we're going to give it a whirl and see how close we can get. Now, we're looking between 0 and 2, and I broke it into 1, 2, 3, 4, 5 chunks. So each one of those chunks is 2/5. So I'm going from 0 to 2/5, from 2/5 to 4/5, 4/5 to 6/5, all the way out to 10/5, which is 2. So I broke it into 5 rectangles. So my width is always going to be 2/5, but notice how my height changes depending on which rectangle I'm on. Now, I did an extra calculation right in here because this is easy. It's always going up by 2/5, but I wanted you to see what's going on here with the height. This is 2 times 1, this is 2 times 2, this is 2 times 3, this is 2 times 4, and this is 2 times 5. That's important because what we're going to do is we're going to take the height times the width, so I get the area of my rectangle. I'm going to do 5 of them and add them up. So that's how we're going to figure out the area underneath this goofy looking curve. Now, you'll notice that I simplified this into 2i, so that I changes 1, 2, 3, 4, 5 to match what's going on here. That's my height, and that's based off of the function. That's how I labeled that height. And the width, I said I was breaking this into equal portions of 2/5. So my width is always going to be 2/5. So let's look at how these calculations work out. Here's my original function. This is what I'm plugging into my original function. So 6 minus this squared. So I have 2i over 5 squared. That's my height. That's how I hit this curved shape each time. My width is always going to be 2/5. So continuing with what we did with sequences and trying to simplify this, I took the 2/5 out front because that's never going to change. That's always there. Now I have a sum from 1 to 5 of 6. That's an easy calculation. It's a constant. 6 times 5 of them. And in here, I did a calculation. 2 squared is 4, I squared, and 5 squared is 25. So I get a 4/25 that I can take out, and I have this I squared. I have a formula for this. It says n times n plus 1 times 2n plus 1, but I know what n is in this case. There are 5 rectangles. So I did some algebra here. I simplified it. I got 44/5. I subtracted these two things with a common denominator and multiplied the 2/5 in. I got 212 over 25, which is roughly 8.48 or 8.5. Now, I could do a rough calculation of this if I go back to the original picture, and I could just plug in a 2. 6 minus 4 is 2. So I've got a height of 6, a width of 2. That's roughly 12. That's too big. We know that. If I take this one, when I plug a 2 in here, now I have 2 times 2, which is 4. 4 is too small, so I know I have to be somewhere between 12 and 4. And I am. I'm at 8.48. But the question you have to ask is, are 5 rectangles enough, or what's going to make this even better? So let's take a look at the definition for the area of a plane region. We talked about these rectangles. We talked about how many do we need. Let's see how they define this formally. So we've got a continuous function f, and it's non-negative on this interval. And notice the interval is closed on both sides. They said the area of the region bounded by the graph of f, so that's the curved line, the x-axis, that's the straight line on the bottom, and the vertical lines x equals a and x equals b. So those two boundaries that we're looking at. So we've got bottom, two sides, and then whatever curves on the top. This is how they define it. Now there's some familiar things here. They've got a width, but notice they didn't divide by 5. They didn't divide by 2. They said divide by n, which can be anything. 10 rectangles, 5 rectangles, however many rectangles we want. That's the width. And we've got a plus b minus a over n times I plugged into the function. This is our height. So it depends on where we're at. But again, notice they don't care how many rectangles we choose. It says we're going to add them up. So we're going to add up the area of each rectangle. And then here's the interesting part. We're going to use the limiting process. And we're going to say we want an infinite number of rectangles. So you can imagine if I tried to draw this, and I'll take my example here. I'm trying to draw rectangles that are about as wide as my pen. So these are all rectangles, and I'm going to find the area of each one of these small rectangles, and I'm going to add them up. And I'm going to say there's an infinite number of rectangles. There's not 5, there's not 20, there's an infinite amount of them. But I'm still adding them up when I find their area. The area is just length times width, or in this case, height times width. So if I take my example that I struggled with there earlier, here's the function. We're going between 0 and 1. So that hasn't changed, and we're trying to find the area under here. But if I can find all of these rectangles and add them all up, I have a great approximation of the area under that curve. Way better than 1 or 0. So I start here with the width. The width says take your ending point minus your starting point and divide by n. So 1 minus 0 divided by n, there's my width. My height, it says I do the same thing that I did for the width, but I multiply it by I, and I add a to it, and that's what gets plugged into the function. So I'm basically starting at a, and I'm adding a certain interval, so a certain distance, but I want the height. So I want it plugged into the function. So I took what I just calculated, 1 over n, and I multiplied it by I, starting at 0, and I got this. So when I plug I over n into the function, remember our function is x squared. So I over n plugged into x squared becomes I squared over n squared. So I have my width, I have my height. So let's find the area. So we need to multiply these two things, and we need to do an infinite amount of them. We need to add them all up. So I multiplied these together. I took the n cubed out because that's just going to be a constant there. It's always going to be there. Here's the part that's changing. Here's the I. I have a formula for n squared, or for I squared. If I want to sum from 1 to n of I squared, I'm going to take n plus 1, 2n plus 1, and divide that by 6. This is how you do that particular summation. Now, I'm going to put my n cubed in, and I'm going to simplify this up here. So I'm going to FOIL this out, distribute the n, put the n cubed in, and I land here. 2n cubed plus a 3n squared plus an n all over 6n cubed. This is that summation notation. What's the last step I need to do? I need to say I want an infinite number of rectangles. Now if this says as n goes to 100, I'm adding up 100 rectangles. If it's at 1,000, I'm adding up 1,000 rectangles. I want to add up all of them. Once we get to this point, the calculations are very easy. I'm going to divide everybody by the largest power of n that I see. This gets divided by n cubed. This gets divided by n cubed. This gets divided by n cubed. And the denominator gets divided by n cubed. Anybody who still has an n left on the bottom are going to go to 0. Anybody who simplifies out, I keep. So I end up with 2/6 simplified down. This area in here is 1/3. Makes sense, it's between 1 and 0, but it's way more accurate because I'm adding up every one of these rectangles. I have an infinite number of rectangles that I'm adding to come up with that area.